Thank you all for joining us. This is one of our, I think our first or second back in-person hybrid meetings, maybe third. So the folks at AMD were kind enough to host us at their relatively newer office. I actually had the privilege of being here when they first opened it pre-pandemic, and I think Lisa and a bunch of other folks, and the mayor of Santa Clara were here, and it is really a lovely office space. We're going to have some opening remarks. I'm going to butcher your name, Ramine.
Yes.
Ramine. And so you're part of the newly formed AI group under Victor Peng.
That's correct.
Right, which I think was announced in the last couple of weeks. So yeah, just please feel free to go ahead, and hopefully we can get your slides shared. And to everyone who's joining us online, hello, good morning, good afternoon, good evening, and thanks for tuning in. And also, just as a reminder, we are recording this, and the first half will be posted online on our YouTube channel. And so, you know, don't burst out and tell us any state secrets.
Thank you so much. So I'm indeed part of the newly formed AI group. My name is Roane, and I manage basically AI product management, ecosystem, and product marketing at AMD. And today I'm going to show you basically what we're doing in AI at the very, very high level. But I will cover some very high level roadmap, and I'll give you also some example of where all in AI we have devices and what kind of model they run. Since this is MLCommons, I think you would be interested in seeing what models are run where and how we could benchmark them. So first, the challenges that we're facing in AI, they're really multiple. I try to bucket them into those 4 different pillars, but basically AI data, the data being processed, but also the compute needs are growing exponentially or hyper exponentially. And as we know, Moore's law is pretty much flattish, and we need to keep up with the compute demand and the data being processed. So we have to continue to grow exponentially when Moore's law is not. So how do we grow more than Moore? That's one challenge, and I will address those during the presentation. The other challenge is that AI is everywhere. Obviously, it's going in every application from cell phones to laptops, to cars, to data center. And this explosion of compute is also likely to create an explosion of power consumption, of energy usage. But that we cannot do, right? It's okay to go exponentially in compute. There is no way we can use an exponentially higher energy year after year. We're pretty much close to saturation planet-wise. So how do we do more compute at the same energy? That's the other challenge. And then finally, the issues of safety bias and compliance are real. As AI is becoming more and more powerful, it's going to get to human level, and then eventually it's going to get slightly smarter than human, and then a lot smarter than human, and then 10 times, 100 times, a million times. It's going to happen over the years, right? Maybe not in our lifetime, but it will get to a point where AI is basically the relationship between the intelligence of AI and humans is going to be the same as between humans and an ant. It will happen, and it's dangerous. And we have to make sure that we self-regulate, but governments will also regulate to make sure that nothing bad happens. So with that in mind, now I'm going to go to products. The products we have AI in are basically, again, from data center to edge and endpoint. We have actually different architectures to cater to different needs of AI. So AMD Instinct GPUs are basically using an architecture called CDNA, that's the compute DNA. And it's using also some Zen cores sometimes. That's our CPU architecture. Like MI300A will have CDNA chiplets and Zen CPU chiplets for HPC, for example. And that really handles the big AI and the big iron data center for HPC and AI, or for just AI like large language model recommendation system and so on. And then we have this architecture XDNA. X comes from Xilinx, which is an architecture we call AI engines internally, which is basically an array of SIMD and VLIW processors that we can program, and we can build custom data flow and custom memory hierarchy. It's not an FPGA, it's really an array of SIMD processors, but it borrows the idea from FPGA to build application-specific data flow and application-specific memory hierarchy. Because in AI, really what's super important is try to minimize the traffic with external memory, with DRAM. You want to stay inside in SRAM as much as possible. If you heard about fused attention or faster transformer, faster, what do they call it again?
Flash attention.
Flash attention, thank you so much. The idea in these things is basically layer after layer. You want to stay inside by saving and reshuffling the data in SRAM inside instead of using the external memory bandwidth. And that's what this architecture does well, XDNA. So we have a small PCIe card for inference in the data center. We have the Xilinx devices that go in automotive and medical devices and so on. And then that same architecture ended up in Ryzen AI, which is a laptop grade CPU. And that's, by the way, for the story, Ryzen AI is already selling in stores, and it started to sell 1 year after the Xilinx acquisition. And it combines Zen from classic AMD, RDNA for graphic GPU, classic AMD, and XDNA from classic Xilinx. 1 year after the acquisition, that's to give you an idea of how fast this field is moving, how fast they taped out a joint architecture and released it. And then on top of those devices that we just saw sits our software stack. Right now, the software stack has different runtimes. So ROCm for GPUs, ZenDNN for CPUs, VitisAI for everything that has XDNA in it. But our goal is to build a unified front end for us and for our customers. For us, because we can't hire 1, 2, 3, 4, 5 times 1,000 software developers to create 5 different flows. And for the customers, because if they want to use 2 different devices, they want to have the same API. But what we realized is that more importantly, it's really very, very important that we partner with open source and work with them to create everything that's around it. There is data processing before you train a network. There is data analytics afterward. There is MLOps and all kind of ecosystem around building and launching a neural network. There's also orchestration. So all the stuff we don't handle, but the ecosystem does, is extremely important. And you all saw that since ChatGPT, obviously LLMs are exploding, but it was really LLMs were proprietary know-how of just a few companies like Google, OpenAI and Microsoft, Facebook. But then end of February, Facebook leaked Llama, their LLM. And then early March, someone from Facebook leaked the training weights of Llama. And then there was an explosion of open source LLM. This is since March, and as I put here, the actual list is too big to represent. This is a small subset of what happened since March of this year. Those are all the open source LLM. And with that come also, so the architecture optimization, we talked about flash attention, multimodal LLM, meaning that it's not just text to text, but text or image or video to text or image or video, and different algorithms, low ranking matrix that can be trained in a bigger LLM that's pre-trained, fine-tuning, reinforcement learning from human feedback, distillation, and so on. And then all the toolings around that, APIs to call those LLM for a program, agents that can take decisions, and LangChain to chain multiple different LLM that have different expertise to do a job for the humans. So there is a pipeline of decision making, and so on and so on. And all of that is available on open source. Like you go to Hugging Face, you have the models, you have the data, and you have all these tools. And so we announced a partnership with Hugging Face, for example, because we realized we have to integrate in all that, and our hardware needs to work with all of that.
Quick time check question. How long is the presentation here?
I have maybe another 10 minutes.
Okay. Yeah, that should be fine.
It's fine.
Perfect.
And then maybe we'll even have time for a couple of questions. And then where are all our devices sitting doing AI? Well, for one thing, on Mars, we literally do have devices in the rover on Mars. That's a self-driving rover. We were also in the landing system, but that wasn't using AI, but it's definitely in the rover. But on Earth also, we have some devices in cars, in automotive, for all the, L2, L2 plus, L3, L4, L5 autonomous driving systems. Right now, we're more like around L2 plus, L3. Tesla is maybe getting close to L3, but as you go up the levels, it becomes more and more autonomous. In healthcare, they use that for image analytics. So their segmentation unit is very popular in healthcare for segmentation, and then their analytics model being run. In industrial, for things like defect detection on a production chain. In communication, so the AI engine actually was first deployed in communication with regular DSP processing for 5G. We had like the first 5G call was made on one of our devices using the AI engine. And now those operators are working on using AI to improve the 5G algorithm, and 6G will definitely use a lot of AI. And that's to improve like the quality of service, the quality of the phone calls, the beam forming, like where to hit the beam, where the few users that are using that beam are, and so on and so on. Those are all going to be get infused with AI, improved with AI. And then in laptops, so I talked about Ryzen AI. So what does the AI part do? Well, right now we're using Teams. So for people who use virtual backgrounds, they use a very quick and dirty model to do the segmentation and the background blur, for example. And you notice that, like, if you have a headset with a wire hanging and you move your head, like between your neck and the wire, you can see the room on the back and all that. But on the new Teams, there are much more solid models running, but they run exclusively on the AI accelerator. If you have a CPU without the AI accelerator, the new model will not run. And then Microsoft also created an eye gaze correction, so you seem to be always paying attention. That also will run only if you have an AI accelerator. So if you have Ryzen AI, it will run. If you have Ryzen, it won't run. And then obviously we're in data center, and those are all the hyperscalers that are using MI200, not the hyperscalers, sorry, the big HPC vendors. So MI250 is in the number one HPC system in the world, supercomputer in the world. We have Lumi, that's the number one in Europe, which is number 3 worldwide. Number 2, I think, is Fujitsu, which is ASIC based. And then even Microsoft deployed just a few hundred of those MI250s, and they have the number 11 supercomputer in the world. So those are all where we are deployed. And I wanted to give you one example in automotive. So we're always saying AI is everywhere, right? Well, it's everywhere, even in a car. It's absolutely crazy what's going on in a car when you look at it in detail. But you have LiDAR and radar system using things like FFTs and Kalman filter for radar, so that's not AI. But for LiDAR and camera fusion, that's definitely AI. They use CNN, 2D convolution, 3D convolution, and so on. And then, I told you I will talk about some models. So this is the slide. The CNNs for cameras, they typically use int8. It's enough accuracy because you can't really estimate the depth and all that super accurately with a few cameras. But with LiDAR, you can. LiDARs are extremely accurate. So for LiDAR, they use more like FP16 or BF16, and for cameras, more int8. int8 is okay. And then for domain controllers, again, that's all vision CNN. But things are moving towards vision transformers because the auto industry is copying Tesla, basically, and Tesla has moved to vision transformers. Notably, there is a transformer that Tesla used that's called BEV for bird eye view. That's to see what's all surrounding you. Interestingly enough, if you have a Tesla, you don't have a bird eye view in your car. You cannot see your car from above with everything that's around, but it's coming. So everybody's moving to BEV transformer because Tesla is. And then someone tweeted that, the Chinese have copied Tesla and done better. And Elon Musk tweeted, well, we're moving away from transformers. We're going to diffusion model. So I put diffusion models because I know it's coming. And diffusion, it's things like stable diffusion. It's using UNets and transformers to basically remove the noise in something. For stable diffusion, for example, you give a prompt. You say, I want a man and a dog walking on the beach. And the model starts with an image that's 100% noise, but it has your prompt, man and dog walking on beach. So it's gonna try to find in the noise where it can see a man, a dog, and the beach and the sea, and it's gonna it's gonna see it, and it's gonna remove more and more noise until it gets to a perfect image. And so how do you use that in a car? They want to use that to remove the noise from the sensors. For example, when you're at night, you have a lot of noise in your camera frames, and they will use basically diffusion models to remove that noise and really see what's going on and see, oops, there is a bicycle here I wasn't seeing, but now that I denoise it, I see it. And then in cabin occupant monitoring, that's make sure you're not. We have an echo. Okay, so that's to make sure you're not sleeping or you're not reading a book while your car is driving. So they use just traditional CNN and RNN there, but I wouldn't be surprised if eventually it goes to transformers as well. And then forward cameras. So we have the object detection with SSD, the classification with ResNet, and mostly MobileNet for cars. And then for segmentation, UNet is mostly used in medical. It's used by some automakers too, but MaskR CNN is very popular. That's a very complex model, extremely complex model. I think it's part of MLTurf, actually.
Yeah, MaskR CNN has been one of our vision models in training since the very beginning.
Yeah. Very big model to implement. Yeah, in terms of technology advancements to basically grow more than more. I showed first how we have different architecture to handle different problem, big problem, medium problem, and small problems. That helps a lot to try to move on that exponential. We basically build architecture, like domain-specific architectures that handle that specific problem, and that allows us to give like a 1.5 to 2x progress every couple of years. But there are also deep down technological improvements, like using advanced packaging, for example. This is a Zen processor. You can see that there are multiple dies, and that helps us optimize the compute better, get better yield, but also get better density. So here we have a lot of SRAMs and IOs. Here we have the compute dies. But then in MI300, that's even better, where you see the dies. So those are the CPU dies, those are GPU dies, and you don't see the IO and the big SRAM because they're sitting underneath. That's real 3D. So underneath, you have a lot of SRAM, you have a lot of IOs, and then on top, that gives us a lot of room to put HBM. And that device has more HBM than any GPU ever announced. And that's advanced 3D packaging enables us with more memory bandwidth, SRAM-wise and HBM-wise and DRAM-wise. So that's also the kind of things we're doing to try to go on an exponential. So basically, that's my conclusion slide. So more than more, we build different domain-specific architecture to be able to optimize specifically for the task at hand, for the application, but also things like advanced packaging helps us there. In terms of supporting AI from endpoints to cloud, we really fine-tune those domain-specific architecture with different data types. For example, we know hyperscaler in the data center, they're doing things like LLMs and recommendation system, and they need bigger data types. For automotive, they mostly need int8. They need some BF16, but we're also trying to do BF16 at a lower cost by basically innovating on the data type side. In terms of sustainability, actually, everything we're doing with the advanced packaging is also helping for lower power. And of course, we work with TSMC to always come up with new processes also to be more power efficient. And in terms of safety, bias, compliance, fairness, and so on, we actually work with the open source community on open data sets that can be tested for fairness, but also that can be permissively licensed. For example, a lot of companies are actually not using things like ChatGPT or Codex or Copilot to generate code, even though it's a huge productivity boost for developers, because they don't know that the data is permissively licensed. They don't want to get sued. Right? A lot of the data actually in ChatGPT and Copilot have parsed GitHub code which are GPL licensed. You don't have the right to take a GPL code and just use it in your product and make money. And that's what's happening when people use those models. So in the open source community, there's code that only filters the permissively licensable code like Apache 2.0 or MIT licensed code, for example. And we make sure that that's what our customers use by partnering with the open source community. We have maybe a couple minutes for questions, if you want. Anything on benchmarking, hardware, software, ecosystem? Yep.
Do you guys have a dedicated group to work on MLPerf for AMD GPUs?
Oh, that's a very good question. I mean, you
try to find the resources to work with.
So you know, you might have noticed we're not very active in publishing for MLPerf. That's because we don't have a dedicated resource. But that's actually something I'm trying to change. So yeah, I kicked off an initiative to start by a small group to do that.
And before you ask the question, can you introduce, after that, can you introduce yourself?
I'm Jeff Liu from Supermicro.
Yeah. Mm-hmm.
Todd Besnick from Initiative. Am I going to be able to get this recording after I leave the room?
I think so.
Yeah. We'll have it on our YouTube channel.
Thank you.
Yeah.
Okay.
Hey, I know Sam, I know Brad, so I've seen a lot of these things.
Oh, okay.
Kurt at MLCommons. I wanted to ask about software support.
Uh-huh.
So it's like, AMD has a lot of new GPUs and other specialized hardware, but if it doesn't run really well and easily in PyTorch and TensorFlow and all the other frameworks coming out, what's AMD's roadmap for making all that be really nice?
Yeah, that's a very good question. So software support and integration in PyTorch. So actually, you might have seen just from a month ago when PyTorch 2.0 came out, for the first time ever, we actually had support on day zero for ROCm that's used for GPUs. So ROCm is now part of PyTorch 2.0. The source code of ROCm is open in the source code of PyTorch 2.0, which is open source. It's the first time ever. So that's a huge deal. And actually, we've been working with the PyTorch Foundation, which is part of the Linux Foundation, for over a year now to make this happen. So on day zero, you had basically support for CUDA and ROCm for the first time. And we're doing that more and more for the other ones too. ZenDNN is open sourced in TensorFlow. So we're working now with Hugging Face and other open source community to make sure that all of our backends are in all of the frameworks, open source frameworks. So we realized this was a problem, yeah, not to have native support and on the first day.
I think we're at time, Peter. Thank you so
Very
much
good.
for hosting us. Thank you for sharing.
So I wanted to talk a bit about how all of the things we're doing fit together. Because I think across the different benchmarks we're developing, the work we're doing with data sets and infrastructure and best practices / standards, there is a coherent thesis that we are pursuing. And that thesis is aligned with our values. And I think these are always worth remembering when we get together. We exist to make the world, or to make ML better for everyone. And we have a philosophy about how we do that. We want to do two things at the same time. One is grow ML markets. The other is make the world a better place. The way I often describe this is we should do projects that when you tell your boss about them, your boss is excited, and when you tell your family about them, your family is excited. Those are things that are really worth doing. And we do this by getting everyone involved, big companies, small companies, academics, NGOs, increasingly folks in the policy world. Then we act through collaborative engineering. We're an organization that builds things. To build those things in a way that serves everyone, we try and make fast decisions, but we try and do them by the MLCommons tradition of grudging consensus, finding a solution that everyone can live with, and we try and do it in a fun and collegial atmosphere so that people enjoy being part of the organization. And this is something I think has really been a strength of us over the last 5 years of our existence. Is we have a lot of people been with MLCommons for almost that entire range. We're constantly attracting new people, and it's because we have a mission that matters, and we do it in a way that's interesting and entertaining to be part of. Today, I particularly want to talk about what it means to act through collaborative engineering and what exactly it is that we are building. We started with a training speed benchmark. And if you think about what a training speed benchmark is, you take some training data, you have a model, you train that reference model on the data to produce a trained model, and you time it, right? And that's something you put in your results, and that's a training speed benchmark. And then we expanded into a whole bunch of different flavors of inference speed, where you start with a trained model, and you apply that to some test data, and you measure how fast that goes. Then we started looking at some things related to measuring the accuracy, and I think in the future, increasingly the safety of a model, okay? And this is where you take some standardized training data, you take a specific model that you're interested in, and this could be something like the models that MedPerf is working on. You train that model, and then you measure its performance on some benchmark data. And benchmark data is very different in character from the test data that you see in public test sets. I downloaded it from the internet, I tested it. We are, I think, going to be leading the effort to define good benchmark data. So this is high quality, diverse, hidden data that you can use to assess how good a particular ML solution is. And that ML solution, you could be focused on the model using this paradigm. You could be focused on the data itself. Like we've fixed the model, we train a whole bunch of different models, we train a fixed model on a whole bunch of different data sets. And we try and understand how you build good data sets. This is what the data perf folks are working on. Or potentially a solution that someone is offering in the marketplace. And that in some ways combines the data, the model, and you're only looking at the trained model and seeing how good that is on your benchmark data. And what that implies is that benchmark data is really critical, and learning how to create hard, diverse benchmarks is important. So we will probably get good at trying to measure benchmark data quality. The data perf element around adversarial data does exactly this. For instance, the Nibbler benchmark, if you saw that announcement, it's basically saying we have a set of trained models and we're trying to create really hard tests for them so that we can find problems and drive progress. But if you stand back, what you see is that we're building an innovation cycle where we're measuring speed and quality of this cyclic set of components. You start with training data, you use it to train your model. You then take that trained model and initially apply it to some test data, perhaps for speed measurement, perhaps just for tuning, and then eventually to some high quality benchmark data before you push it out into the world because you want to know whether it works. And all of that information goes into a set of results that is a really powerful information resource for researchers and for customers. And that set of results is not just an end product. It's not, hey, we have results, tell the marketing people, to go out and proclaim how great we are. It's also information that drives improvement. It's how we know what needs to be changed in the models. It's how we know what needs to be changed in the training data. It's how we realize that we have something that's missing from our benchmark data that needs to get better. It's how we know where systems are fast and where systems are slow and how we should optimize that. And this innovation cycle is a industry ecosystem level impact. It cuts across companies, it cuts across software, it cuts across hardware, and it's something that we are all coming together to build and enable. And as we continue to grow as an organization, I think the next year or two will see significant growth, especially into quality safety measurements. We need to be able to take this cycle and efficiently scale it to do a variety of different things. Right now, when we bring up a new working group, they often end up creating infrastructure from scratch, and we really want them to be able to leverage shared infrastructure. We already have some start on this. For instance, the results submission infrastructure that's shared across inference and training, but I think we're going to need to get more and more of this to enable us to support a wider and wider range of activities as the AI industry grows at its exponential rate. And one of the ways that we make that happen is to use the infrastructure to automate things. And the way that we ensure that everything can engage with that automation is the work we're doing with best practices. Things like MLCube. MedPerf wouldn't be possible without MLCube. We have other efforts like the collective mind effort, the new croissant dataset format, which could really enable data tooling and data research. And these best practices serve as the interface layer between all the things that are happening in the ML world and people like us looking to build infrastructure that delivers value across that range of things. So this picture, I think, tries to summarize what we're all here together to build, which is this innovation cycle that is very scalable and moves very quickly to keep up with the times we find ourselves in. And we do that through collaborative engineering, because coming together, we can build something that is bigger than anything we could build alone. And I mean that not only as individuals, but also as organizations. We need this cycle to define and guide the crazy growth of AI and ML that we are all engaged in, to provide products that serve our customers and benefit society. And to do that, we need to bring a bunch of different organizations together. So really glad that all of you are here trying to help us do that. This may be dating myself, but I don't know how many people recognize the robot pictured here, but this is a classic anime cartoon when I was growing up, where they would always confront some bad guy and they couldn't defeat the bad guy individually, but if they came together and formed this robot, the Voltron, they could defeat the bad guy. And you know, that was basically every episode. But I think there's a lot of truth in it, especially for the scale of the challenges and the opportunities we face in machine learning. So glad to be working with all of you to try and assemble our particular Voltron. And with that, I will hand it over to David to tell us how the assembly is going.
Yes. As it turns out, the hand bone has been connected to the head bone. No, actually, things are going great. So first, I want to start by welcoming in our new members. You know, MLCommons is a member-driven organization. So, you know, everyone here is, well, not everyone, but most folks here are from member companies. And so we want to thank you for getting involved. Oracle and ConnectTech just joined very recently. CoreWeave joined maybe about a month or two ago. And we'll see a little bit more, but they participated in MLPerf training. So welcome aboard. We also have a couple of new working group chairs that I want to call out. Let's see, Tushar, for the sake of time, I'm going to introduce you, if that's all right.
Yep, that's all
right. Perfect. Or actually, oh, hold on, wait, wow, okay, this is way better than our current AV. Actually, why don't you give it a try? Why don't you and Srinivas try it? Like, go for like a minute each and tell me when you want me to switch the slide.
Sounds good. So hi everybody, my name is Tushar Krishna. I'm a faculty member at Georgia Tech, very excited to be part of MLCommons. I'm going to be co-chairing this new research working group called Chakra. We actually just kickstarted it earlier this week, where the focus is to standardize the collection of execution traces to feed simulators, emulators, and replay benchmarks. My broad research is in computer architecture. I look a lot at distributed ML systems, machine learning accelerators, custom accelerators, specifically focusing on the interconnection network fabrics. You know, as part of the overall ML ecosystem, my group has been working a lot on developing and maintaining open source simulation infrastructures. So things like AstroSim, which is a distributed training simulator, and Maestro and ScaleSim, which are inference simulators. So looking forward to working with you all. I think hopefully in the next year's version, we'll actually have some updates from our working group as well. Nice to meet you.
Awesome. Welcome aboard, Tushar. And Srinivas, now you're on.
Hi, folks. I'm Srinivas. I'm a research scientist and tech lead at Meta. I was instrumental in deploying the current set of GPU AI clusters and introducing RDMA at production scale in Meta. I'm also currently responsible for scaling networking communication libraries and observability tools across the entire production scale for Meta AI clusters. On the open source side, I've led the co-development of Param benchmarks, AstroSim with Tushar and the UCC communication library. I think Tushar already gave an introduction on Chakra, and looking forward to working with this broad team here to making that impact.
All right, perfect, and welcome aboard. I'll be talking about briefly about the Chakra working group in a little bit. All right, so I want to run a little bit of a victory lap here. So these are all the things we got done in Q2. Some of this is maybe stealing a little bit from Q3. But, you know, most prominently, we'll talk about this a little bit later. We have MLPerf training and Tiny results that were released in Q2. Q2 at the end of Q2. This includes our new GPT-3 training benchmark and DLRM DCN v2. So that's our second generation recommendation benchmark. Both of these, I'm like really proud of the team for getting those delivered, especially GPT-3 was a massive lift. Just as an aside, well, we'll talk about it more in detail. We launched the MLPerf storage benchmark. So this is how do we measure the storage performance of systems that feed into training. This is now open for submission. We'll have some discussion from this a little bit later from Curtis, our chair. Science Working Group put out a call for participation. We got a publication in Nature on the MedPerf project, and that's been very widely cited. Kelly, our head of marketing, did a great push around that. We had fantastic collaboration from, I think there's like 60 or 70 people on the paper. It's not quite CERN level of publication, but it was, you know, a lot of coordination, a lot of momentum, a lot of interest, and a lot of potential impact. Related, there's a project called Gandalf, which is focused on how to make AI more usable to medical researchers that is somewhat coupled to MedPerf. That was also announced this quarter. Last, we put out a public announcement of our collaboration with ABCC on developing the first automotive-focused ML benchmark, and that's well underway and making rapid progress. The Chakra Working Group launched. They actually had their first meeting earlier this week. There were 50 people in that meeting, which is really fantastic. You know, that's like sort of the level of attendance we had on some of the first MLPerf meetings. Now, the one thing I would mention is in the first MLPerf meetings, we bribed everyone with food to show up. You know, this was all virtual, so they weren't coming for the food. And then we're also getting started on our website redesign. So, you know, I'm very excited about that. So diving a little bit into the MLPerf training results, we had 3 new submitters, 16 submitters total, over 250 results, significant improvements in performance. The geo mean of the performance improvement was about 30%, just for those who are curious. We had our new recommendation and LLM benchmark. We had 3 submitters to GPT-3 and 5 to our new recommender. Just as a interesting aside, someone in the press asked me, you know, well, it sounds like a lot of work to actually build the GPT-3 benchmark. And so I got to digging into this a little bit, and it turns out that we spent something over 600,000 accelerator hours building the benchmark. And I believe that roughly speaking, there was sort of an internal estimate that this was about 1.5x-ish, you know, the original full training for GPT-3. And again, this is studying convergence. This is one of the things that I really want to highlight is, you know, it sounds easy to just grab some code and slap some mental calipers on it and measure it, but you can't actually do that in AI. AI benchmarking is real hard work. It takes real compute and real talent. And, you know, that goes especially for something at scale like GPT-3. It's also true for things like our recommender, which the folks from Facebook really helped to lead. We also had the tiny results on the opposite end of the spectrum. Rather than figuring out how we can use 20 kilowatts, we're trying to figure out how we can use 20 microwatts here. We got a ton of new submitters, over 150 results, 7 new submitters. Very excited about this as well. And Kelly, our head of marketing, put together a fantastic coverage report. So we got over 200 stories. A lot of those were from our press release, you know, something like about 170 of them, right? And so those are going to be direct copies of the press release we put out. But what that means is, you know, there's something like 35 folks who are writing tailored stories specifically about MLPerf and about the MLPerf results. Fairly high level of interest, and we've got a selection of them up here. I also want to announce the MLCommons Hero Awards. So just to highlight folks who have made particular contributions in the last quarter. One is An Nguyen, who I don't know if he's tuning in. He is in Germany. He works with the MLPerf mobile group and really handles a lot of the ML side over there, as well as some of the higher level complexities around benchmarking and our results portal. So he's absolutely integral to the MLPerf mobile effort, which is working on an app for Android and iOS. I am probably going to butcher these names, but Pierre and Juice worked on the croissant format converter and validator. Oops, there's a typo in there. I'll fix that later. So croissant is sort of, the idea is how can we get a standardized format for ML data sets that both contains the data and then describes the ML relevant attributes of it. And so they did this sort of spun up under our datasets working group recently, and they did some of the initial work. And then I want to call out Nusha Ardlani and Praveen Paratosh. Praveen is actually here. Nusha is not here. Nusha is probably on mat leave at the moment. So for those who don't know, they led DataPerf, and Nusha in particular did this while, DataPerf just sort of landed very recently, and she also landed her first child. Doing that while you're pregnant and coordinating everything, heroic lift from Nusha and Praveen as well. DataPerf is sort of, the question is if you want to run an ML competition where instead of twiddling the model to maximize accuracy, you're twiddling the data set, that's what DataPerf is. So great efforts for everyone there. And then I want to briefly talk about the upcoming MLCommons Rising Stars program. So our research working group, not research working group, but MLCommons started out with both academic and industrial collaborators. One of the things that we saw as an opportunity is that there are many Rising Star programs focused on like EE students or CS students. And what we wanted was something that was at the intersection of systems and machine learning to call out sort of early stage researchers who are doing great and relevant work. So in August, we're going to have a 2-day workshop. We're going to have the Rising Stars are coming out to Silicon Valley to present some of their work. For folks who are in the MLCommons community, this is funded by MLCommons dollars. And one of the points is we'd actually like to connect you up to the Rising Stars, both for recruiting, for sponsorship. If their research is relevant to you, it would be great to have you connect and build those connections between research and industry. The event is on August 17th and 18th. And like I said, there'll be 35 in this first cohort. And we have some great data on diversity, although this may be a little bit hard to read. But first of all, we've got, so this is a bunch of diversity stats looking at where folks are in their academic careers in terms of how many years in are they? Are they a postdoc? Are they early, in their PhD program? We've got a wide variety of schools. We've got 34% folks who identify as women, which is actually pretty good. It could be better, but if you compare that to sort of the standard, like that's actually pretty good, right? Like the reality is that machine learning is a heavily male-dominated field, and it's awesome to see what we can do to encourage folks who are underrepresented. We also have some stats on over 40% are folks from underrepresented groups. So that's that. And that brings us to a big thank you to all of our members who help make this community fantastic. You guys give us the funding, you give us the engineering, you give us the ideas, and really help to make ML better for everyone, as we said. And at that point, we've got a probably not quite 20-minute break, but we'll be back at 10:20. How did I do on time? What time is it?
9:56. 23 minutes.
Oh, whoa. So I finished ahead of time. All right. Just goes to show, so once you start measuring performance improves.
That's right.
All right. So look, we can take a couple minutes. And does anyone have any questions? Either if someone's online and wants to type in the chat, and maybe we can monitor that, or anyone here. Anyone have any questions? We can also just go to the break. I'm more than happy to stand off the hot seat.
Are we gonna turn the microphone off in the break too?
I don't know. So the one thing I will say is the next thing is the working group update. So if you are a working group chair, go check out the slide deck, see where you are. Each working group is going to be talking for, I think, about three or so minutes. But you'll want to make sure that you are there to talk about what your working group is doing. Otherwise, I will make up nonsense according to your slides.
Use the mic.
Yeah, we can probably do that. I don't.
If you're in Teams, then you can just be.
Well, no. But I don't know if this is the mic that's broadcasting. I think the room is mic'd up. Yeah.
I'll have you mute it.
Yeah. So we're gonna go for a break.